Welcome to this fifth course on deep learning. In this course, you learn about sequence models, one of the most exciting areas in deep learning. Models like recurrent neural networks, or RNNs, have transformed speech recognition, natural language processing, and other areas. And in this course, you learn how to build these models for yourself. Let's start by looking at a few examples of what sequence models can be useful. In speech recognition, you are given an input audio clip, X, and asked to map it to a text transcript, Y. Both the input and the output here are sequence data because X is an audio clip, so that plays out over time, and Y, the output, is a sequence of words. So sequence models, such as recurrent neural networks and other variations you learn about in a little bit, have been very useful for speech recognition. Music generation is another example of a problem with sequence data. In this case, only the output Y is a sequence. The input can be the empty set, or it can be a single integer, maybe referring to the genre of music you want to generate, or maybe the first few notes of the piece of music you want. But here, X can be nothing, or maybe just an integer, and the output Y is a sequence. In sentiment classification, the input X is a sequence. So given an input phrase like, "There's nothing to like in this movie," how many stars do you think this review would be? Sequence models are also very useful for DNA sequence analysis. So your DNA is represented via the four alphabets A, C, G, and T. And so given a DNA sequence, can you label which part of this DNA sequence, say, corresponds to a protein? In machine translation, you are given an input sentence, "Voulez-vous chanter avec moi?" and you're asked to output the translation in a different language. In video activity recognition, you might be given a sequence of video frames and asked to recognize the activity. And in named entity recognition, you might be given a sentence and asked to identify the people in that sentence. So all of these problems can be addressed as supervised learning with label data X, Y as the training set. But as you can tell from this list of examples, there are a lot of different types of sequence problems. In some, both the input X and the output Y are sequences, and in that case, sometimes X and Y can have different lengths, or in this example and this example, X and Y have the same length. And in some of these examples, only either X or only the output Y is a sequence. So in this course, you learn about sequence models that are applicable to all of these different settings. So I hope this gives you a sense of the exciting set of problems that sequence models might be able to help you to address. With that, let's go on to the next video where we start to define the notation we'll use to define these sequence problems. In the last video, you saw some of the wide range of applications to which you can apply sequence models. Let's start by defining a notation that we'll use to build up these sequence models. As a motivating example, let's say you want to build a sequence model to input a sentence like this: "Harry Potter and Hermione Granger invented a new spell." And these are characters, by the way, from the Harry Potter sequence of novels by J.K. Rowling. And let's say you want a sequence model to automatically tell you where are the people's names in this sentence. So this is a problem called named entity recognition, and this is used by search engines, for example, to index all of, say, the last 24 hours news of all the people mentioned in the news articles so that they can index them appropriately. And name entity recognition systems can be used to find people's names, companies' names, times, locations, countries' names, currency names, and so on in different types of text. Now, given this input X, let's say that you want a model to output Y that has one output per input word, and the target output, the desired Y, tells you for each of the input words, is that part of a person's name? And technically, this maybe isn't the best output representation. There are some more sophisticated output representations that tells you not just is a word part of a person's name, but tells you where are the start and ends of people's names in a sentence. So you might want to know Harry Potter starts here and ends here, starts here and ends here. But for this motivating example, I'm just going to stick with this simpler output representation. Now, the input is a sequence of 9 words. So eventually, we're going to have 9 sets of features to represent these 9 words. And to index into the positions in the sequence, I'm going to use X and then superscript angle brackets 1, 2, 3, and so on, up to x angle bracket 9 to index into the different positions. I'm going to use xt with an index t to index into positions, in the middle of the sequence. And t implies that these are temporal sequences, although whether the sequence is a temporal one or not, I'm going to use the index t to index into the positions in the sequence. And similarly, for the output, we're going to refer to these outputs as y angle bracket 1, 2, 3, and so on, up to y9. Let's also use t subscript x to denote the length of the input sequence. So in this case, there are 9 words, so tx is equal to 9, and we'll use ty to denote the length of the output sequence. In this example, tx is equal to ty, but as you saw in the last video, tx and ty can be different. So you will remember that in the notation we've been using, we've been writing x round brackets I to denote the ith training example. So to refer to the tth element, or the tth element in the sequence of training example I, we'll use this notation. And if tx is the length of a sequence, then different examples in your training set can have different lengths. And so txi will be the input sequence length for training example I. And similarly, yit means the tth element in the output sequence of the ith training example, and tyi will be the length of the output sequence in the ith training example. So in this particular example, txi is equal to 9, but if you had a different training example with a sentence of 15 words, then txi would be equal to 15 for that different training example. Now that we're starting to work in NLP, or natural language processing, now this is our first serious foray into NLP, or natural language processing. And one of the things we'll need to decide is how to represent individual words in a sequence. So how do you represent a word like Harry, and what should x1 really be? Let's next talk about how we would represent individual words in a sentence. So to represent the words in a sentence, the first thing you do is come up with a vocabulary, sometimes also called a dictionary, and that means making a list of the words that you will use in your representation. So the first word in the vocabulary is a. That's really the first word of the dictionary. The second word is Aaron. And then a little bit further down is the word and then eventually you get to the word Harry, then eventually the word Potter, and then all the way down to maybe the last word in the dictionary is Zulu. And so A would be word 1, Aaron is word 2, and in my dictionary, the word and appears in position or index 367. Harry appears in position 4075, Potter at position 6830, and Zulu, if the last word of the dictionary is maybe word 10,000. So in this example, I'm going to use a dictionary with size 10,000 words. This is quite small by modern NLP applications. For commercial applications, for reasonable sized commercial applications, dictionary sizes of 30 to 50,000 are more common, and 100,000 is not uncommon. And then some of the large internet companies will use dictionary sizes that are maybe 1 million words or even bigger than that. But you see a lot of commercial applications use dictionary sizes of maybe 30,000 or maybe 50,000 words. But I'm going to use 10,000 for illustration since it's a nice round number. So if you have chosen a dictionary of 10,000 words, and one way to build this dictionary would be to look through your training sets and find the top 10,000 occurring words, or to look through some of the online dictionaries that tells you what are the most common 10,000 words in the English language, say. What you can do is then use one-hot representations to represent each of these words. For example, x1, which represents the word Harry, would be a vector with all zeros except for a 1 in position 4075, because that was the position of Harry in the dictionary. And then x2 will be again similarly a vector of all zeros except for a 1 in position 6830, and then zeros everywhere else. The word and was represented as a position 367, so x3 would be a vector with zeros, a 1 in position 367, and then zeros everywhere else. And each of these would be a 10,000 dimensional vector if your vocabulary has 10,000 words. And this one, A, I guess, because A is the first word of the dictionary, then x7, which corresponds to the word A, that would be the vector 1. This is the first element of the dictionary, and then 0 everywhere else. So in this representation, xt for each of the values of t in your sentence will be a one hot vector. One hot because there's exactly 1 1 that's on and zeros everywhere else, and you would have 9 of them to represent the 9 words in this sentence. And the goal is, given this representation for x, to learn a mapping using a sequence model to the target output y. And we'll do this as a supervised learning problem when we're given labeled data with both x and y. And just one last detail, which we'll talk more about in a later video, is what if you encounter a word that is not in your vocabulary? Well, the answer is you create a new token or a new fake word called unknown word, which I'm to denote as follows, angle brackets UNK, to represent words not in your vocabulary. But we'll come more to talk more about this later. So to summarize, in this video, we described a notation for describing your training set for both x and y for sequence data. In the next video, let's start to describe a recurrent neural network for learning the mapping from x to y. In the last video, you saw the notation we'll use to define sequence learning problems. Now, let's talk about how you can build a model, build a neural network to learn the mapping from x to y. Now, one thing you could do is try to use a standard neural network for this task. So in our previous example, we had 9 input words. So you could imagine trying to take these 9 input words, maybe the 9 one-hot vectors, and feeding them into a standard neural network, maybe a few hidden layers, and then eventually have this output, the 9 values, 0 or 1, that tell you whether each word is part of a person's name. But this turns out not to work well, and there are really 2 main problems with this. The first is that the inputs and outputs can be different lengths in different examples. So it's not as if every single example had the same input length tx or the same output length ty. And maybe if every sentence had a maximum length, maybe you could pad or zero pad every input up to that maximum length, but this still doesn't seem like a good representation. And then a second, and maybe more serious problem, is that a naive neural network architecture like this, it doesn't share features learned across different positions of text. In particular, if the neural network has learned that maybe the word Harry appearing in position 1 gives a sign that that's part of a person's name, then won't it be nice if it automatically figures out that Harry appearing in some other position xt also means that that might be a person's name. And this is maybe similar to what you saw in convolutional neural networks, where you want things learned for one part of the image to generalize quickly to other parts of the image, and we like a similar effect for sequence data as well. And similar to what you saw with ConvNets, using a better representation will also let you reduce the number of parameters in your model. So previously we said that each of these is a 10,000 dimensional one hot vector, and so this is just a very large input layer. If the total input size was, maximum number of words times 10,000, and the weight matrix of this first layer would end up having an enormous number of parameters. So a recurrent neural network, which we'll start to describe in the next slide, does not have either of these disadvantages. So what is a recurrent neural network? Let's build one up. So if you are reading the sentence from left to right, the first word you would read is some first word, say x1. And what we're going to do is take the first word and feed it into a neural network layer. I'm going to draw it like this. So that's a hidden layer of the first neural network. And we can have the neural network maybe try to predict the output. So is this part of a person's name or not? And what a recurrent neural network does is when it then goes on to read the second word in the sentence, say x2, instead of just predicting y2 using only x2, it also gets to input some information from what it had computed at time step 1. So in particular, the activation value from time step 1 is passed on to time step 2. And then at the next time step, a recurrent neural network inputs the third word x3, and it tries to predict, output some prediction, y hat 3, and so on, up until the last time step where it inputs x, tx, and then it outputs y hat, ty. At least in this example, tx is equal to ty, and the architecture will change a bit if tx and ty are not identical. And so at each time step, the recurrent neural network passes on its activation to the next time step for it to use. And to kick off the whole thing, we'll also have some made-up activation at time 0. This is usually the vector of zeros. Some researchers will initialize A0 randomly. You have other ways to initialize A0, but really having a vector of zeros as the fake time 0 activation is the most common choice. And so that gets input to the neural network. In some research papers or in some books, you see this type of neural network drawn with the following diagram, in which at every time step you input x and output y hat. Maybe sometimes there'll be a t index there, and then to denote the recurrent connection, sometimes people will draw a loop like that the layer feeds back to itself. Or sometimes they'll draw a shaded box to denote that this is the shaded box here denotes a time delay of 1 step. I personally find these recurrent diagrams much harder to interpret, and so throughout this course I'll tend to draw the unrolled diagram like the one you have on the left. But if you see something like the diagram on the right in a textbook or in a research paper, what it really means, or the way I tend to think about it, is to mentally unroll it into the diagram you have on the left instead. The recurrent neural network scans through the data from left to right, and the parameters it uses for each time step are shared. So there'll be a set of parameters, which we'll describe in greater detail on the next slide, but the parameters governing the connection from x1 to the hidden layer will be some set of parameters we're going to write as WAX, and is the same parameters WAX that it uses for every time step. I guess you could write WAX there as well. And the activations, the horizontal connections, will be governed by some set of parameters WAA. And it's the same parameters WAA used on every time step. And similarly, there's some WYA that governs the output predictions. And I'll describe on the next slide exactly how these parameters work. So in this recurrent neural network, what this means is that when making the prediction for y3, it gets the information not only from x3, but also the information from x1 and x2, because the information from x1 can pass through this way to help the prediction with y3. Now, one weakness of this RNN is that it only uses the information that is earlier in the sequence to make a prediction. In particular, when predicting y3, it doesn't use information about the words x4, x5, x6, and so on. And so this is a problem because if you're given a sentence, he said Teddy Roosevelt was a great president, In order to decide whether or not the word Teddy is part of a person's name, it'd be really useful to know not just information from the first two words, but to know information from the later words in the sentence as well. Because the sentence could also have been, he said, teddy bears are on sale. And so, given just the first three words, it's not possible to know for sure whether the word teddy is part of a person's name. In the first example, it is. In the second example, it's not. But you can't tell the difference if you look only at the first three words. So one limitation of this particular neural network structure is that the prediction at a certain time uses inputs or uses information from the inputs earlier in the sequence, but not information later in the sequence. We will address this in a later video where we talk about bidirectional recurrent neural networks, or BRNNs. But for now, this simpler unidirectional neural network architecture will suffice to explain the key concepts. And we'll just have to make a quick modification to these ideas later to enable, say, the prediction of y hat 3 to use both information earlier in the sequence as well as information later in the sequence. But we'll get to that in a later video. So let's now write out explicitly what are the calculations that this neural network does. Here's a cleaned up version of the picture of the neural network. As I mentioned previously, typically you started off with the input A0 equals the vector of all zeros. Next, this is what forward propagation looks like. To compute A1, you would compute that as an activation function G applied to WAA times A0 plus WAX times X1 plus a bias, which we're going to write as BA, and then to compute y hat 1, the prediction at time step 1, that will be some activation function, maybe a different activation function than the one above, but applied to WYA times A1 plus BY. And the notation convention I'm going to use for the substrate of these matrices, like that example, WAX, the second index means that this WAX is going to be multiplied by some X-like quantity, and this A means that this is used to compute some A-like quantity, like so. And similarly, you notice that here, WYA is multiplied by some A-like quantity to compute, a Y-type quantity. The activation function used in to compute the activations will often be a tanh in the choice of an RNN, and sometimes ReLUs are also used, although there's a but tanh is actually a pretty common choice, and we have other ways of preventing the vanishing gradient problem, which we'll talk about later this week. And depending on what your output y is, if it is a binary classification problem, then I guess you would use a sigmoid activation function, or it could be a softmax if you have a k-way classification problem. But the choice of activation function here would depend on what type of output y you have. So for the name entity recognition task, where y was either 0 or 1, I guess the second g could be a sigmoid activation function. And I guess you could write, G2 if you want to distinguish that this is these could be different activation functions, but I usually won't do that. And then more generally, at time t, AT will be G of WAA times A from the previous time step plus WAX of X from the current time step plus BA, and Y hat T is equal to G, again, could be different activation functions, but G of WYA times AT plus BY. So these equations define forward propagation in the neural network, where you would start off with A0 as a vector of all zeros, and then using A0 and X1, you would compute A1 and Y hat 1, and then you take X2 and use X2 and A1 to compute A2 and Y hat 2, and so on, and you carry out forward propagation going from the left to the right of this picture. Now, in order to help us develop the more complex neural networks, I'm actually going to take this notation and simplify it a little bit. So let me copy these two equations to the next slide. Right, here they are. And what I'm going to do is actually so to simplify the notation a bit, I'm actually going to take that and write in a slightly simpler way. And so I'm going to write this as AT equals G times just a matrix WA times a new quantity, which is going to be AT minus 1, comma, XT, and then plus BA. And so that underlying quantity on the left and right are supposed to be equivalent. So the way we define WA is we'll take this matrix WAA and this matrix WAX and put them side by side, kind of stack them horizontally as follows, and this will be the matrix WA. So for example, if A was a 100-dimensional, and in our running example, X was 10,000 dimensional, then WAA would have been a 100 by 100 dimensional matrix, and WAX would have been a 100 by 10,000 dimensional matrix. And so stacking these two matrices together, this would be 100 dimensional, this would be 100, and this would be, I guess, 10,000 elements. So WA will be a 100 by 10100 dimensional matrix. Right? I guess this diagram on the left is not drawn to scale, right? Since WAX would be a very wide matrix. And what this notation means is to just take the two vectors and stack them together. So we're going to use that notation to denote that we're going to take the vector AT minus 1, so that's a 100-dimensional, and stack it on top of AT. So this ends up being a 10100 dimensional vector. And so hopefully you can check for yourself that this matrix times this vector just gives you back the original quantity, right? Because now this matrix WAA times WAX multiplied by this AT minus 1 XT vector, this is just equal to WAA times AT minus 1 plus WAX times XT, which is exactly what we had back over here. So the advantage of this notation is that rather than carrying around two parameter matrices, WAA and WAX, we can compress them into just one parameter matrix, WA. And this will simplify our notation for when we develop more complex models. And then for this, in a similar way, I'm just going to rewrite this slightly. I'm going to write this as WY AT plus BY. And now we just have the subscripts in the notation, WY and BY. It denotes what type of output quantity we're computing. So WY indicates that that's a weight matrix for computing a Y-like quantity. And here WA and BA on top indicates those are the parameters for computing, like an activation output quantity. So that's it. You now know what is a basic recurrent neural network. Next, let's talk about backpropagation and how you would learn with these RNNs. You've already learned about the basic structure of an RNN. In this video, you see how backpropagation in a recurrent neural network works. As usual, when you implement this in one of the programming frameworks, often the programming framework will automatically take care of backpropagation. But I think it's still useful to have a rough sense of how backprop works in RNNs. Let's take a look. You've seen how for forward prop, you would compute these activations from left to right as follows in the neural network until you've output all of the predictions. In backprop, as you might already have guessed, you end up carrying backpropagation calculations in basically the opposite direction of the forward prop arrows. So let's go through the forward propagation calculation. You're given this input sequence x1, x2, x3, up to tx, and then using x1 and say a0, you're going to compute the activation at time step 1, and then together x2 together with a1 I use to compute a2, and then a3, and so on up to atx. Alright, and then to actually compute a1, you also need the parameters. I'll just draw this in green, wa and ba. Those are the parameters that I use to compute a1. And then these parameters are actually used for every single time step. So these parameters are actually used to compute a2, a3, and so on. All the activations up to last time step depend on the parameters wa and ba. Let's keep fleshing out this graph. Now, given a1, your neural network can then compute the first prediction y hat 1, and then at the second time step y hat 2, y hat 3, and so on with y hat ty here. And let me again draw the parameters of a different color. So to compute y hat, you need the parameters wy as well as by, and this goes into this node as well as all the others. I guess I just draw this in green as well. Next, in order to compute backpropagation, you need a loss function. So let's define an element-wise loss first, which is, suppose that for a certain word in the sequence, it is a person's name, so maybe yt is 1, and your neural network outputs some probability, maybe 0.1 of that particular word being a person's name. Right? So I'm going to define this as the standard logistic regression loss, also called the cross-entropy loss. This will look familiar to you from when we were previously looking at binary classification problems. So this is the loss associated with a single prediction at a single position, or the single time step t for a single word. Let's now define the overall loss for the entire sequence. So L will be defined as the sum overall t equals 1 to, I guess, tx or ty. Tx is equal to ty in this example, of the losses for the individual time steps, comma, y, t. And then, so this capital L, without this superscript t, this is the loss for the entire sequence. So in a computation graph, to compute the loss given y hat 1, you can then compute the loss for the first time step. Given that, you compute the loss for the second time step, the loss for the third time step, and so on, the loss for the final time step. And then lastly, to compute the overall loss, we will take these and sum them all up to compute the final L using that equation, which is the sum of the individual per time step losses. So this is the computation graph. And from the earlier examples you've seen of backpropagation, it shouldn't surprise you that backprop then just requires doing computations or passing messages in the opposite directions to all of the forward propagation steps arrows. And so you end up doing that. And that then allows you to compute all the appropriate quantities that lets you then take derivatives with respect to the parameters and update the parameters using gradient descent. Now, in this backpropagation procedure, the most significant messages to be passed, the most significant recursive calculation is this one, which goes from the right to the left. And that's what gives this algorithm as well a pretty fanciful name called backpropagation through time. And motivation for this name is that for forward prop, you're scanning from left to right in increasing indices of the time t, whereas for backpropagation, you're going from right to left, kind of going backwards in time. So this gives this, I think, really cool name, backpropagation through time, where you're going backwards in time, right? That phrase really makes it sound like you need a time machine to implement this algorithm, but I always thought that backprop through time was just one of the coolest names for an algorithm. So hope that gives you a sense of how forward prop and backprop in an RNN works. Now, so far, you've only seen this main motivating example of an RNN in which the length of the input sequence was equal to the length of the output sequence. In the next video, I want to show you a much wider range of RNN architectures that'll let you tackle a much wider set of applications. Let's go on to the next video. So far, you've seen an RNN architecture where the number of inputs, Tx, is equal to the number of outputs, Ty. It turns out that for other applications, Tx and Ty may not always be the same, and in this video, you see a much richer family of RNN architectures. You might remember this slide from the first video of this week, where the input X and the output Y can be many different types. And it's not always the case that Tx has to be equal to Ty. In particular, in this example, Tx can be length 1 or even an empty set. And then in an example like movie sentiment classification, the output Y could be just an integer from 1 to 5, whereas the input is a sequence. And in name entity recognition, in the example we're using, the input length and the output length are identical, but there are also some problems where the input length and the output length can be different. They both are sequences but have different lengths, such as machine translation, where a French sentence and an English sentence can need different numbers of words to say the same thing. So it turns out that we could modify the basic RNN architecture to address all of these problems. And the presentation in this video was inspired by a blog post by Andrej Karpathy titled The Unreasonable Effectiveness of Recurrent Neural Networks. Let's go through some examples. The example you've seen so far used Tx equals Ty, where we had an input sequence x1, x2, up to xtx, and we had a recurrent neural network that worked as follows, where we would input x1 to compute y hat 1, y hat 2, and so on up to y hat ty as follows. And in earlier diagrams, I was drawing a bunch of circles here to denote neurons, but I'm just going to omit those little circles for most of this video, just to make the notation simpler. So this is what you might call a many-to-many architecture, because the input sequence has many inputs as a sequence, and the output sequence also has many outputs. Now let's look at a different example. Let's say you want to address sentiment classification. Here, X might be a piece of text, such as it might be a movie review that says, there is nothing to like in this movie. So X is going to be a sequence, and Y might be a number from 1 to 5, or maybe 0 or 1. Is this a positive review or a negative review? Or it could be a number from 1 to 5. Do you think this is a 1-star, 2-star, 3, 4, or 5-star review? So in this case, we can simplify the neural network architecture as follows. We could have an input x1, x2, so input the words one at a time. So if the input text was, there is nothing to like in this movie, so there is nothing to like in this movie would be the input. And then rather than having to use an output at every single time step, we can then just have the RNN read in the entire sentence and have it output Y at the last time step when it has already input the entire sentence. So this neural network would be a many-to-one architecture, because it has many inputs, it inputs many words, and it just outputs one number. For the sake of completeness, there is also a 1-to-1 architecture. So this one is maybe not terribly, less interesting. It's more like a standard neural network. We have some input X and just have some output Y. And so this would be the type of neural network that we covered in the first 2 courses in this sequence. Now, in addition to many-to-one, you can also have a one-to-many architecture. So an example of a one-to-many neural network architecture will be music generation. And in fact, you get to implement this yourself in one of the programming exercises for this course, where your goal is to have a neural network output a set of notes corresponding to a piece of music. And the input X could be maybe just an integer telling it what genre of music you want or what's the first note of the music you want. And if you don't want to input anything, X could be a null input or could always be the vector of zeros as well. For that, the neural network architecture would be you input X and then have your RNN output the first value and then have that with no further inputs output the second value and then go on to output the third value and so on until you've synthesized the last note of the musical piece. And if you want, you can have this input A0 as well. One technical note, what you see in a later video is that when you're actually generating sequences, often you take this first synthesized output and feed it to the next layer as well. So the network architecture actually ends up looking like that. So we've talked about many-to-many, many-to-one, one-to-many, as well as one-to-one. It turns out there's one more interesting example of many-to-many, which is worth describing, which is when the input and the output lengths are different. So in the many-to-many example you saw just now, the input length and the output length have to be exactly the same. But for an application like machine translation, the number of words in the input sentence, say a French sentence, and the number of words in the output sentence, say the translation into English, those sentences could be different lengths. So here's an alternative neural network architecture where you might have a neural network first read in the sentence. So first read in the input, say French sentence that you want to translate to English, and then having done that, you then have the neural network output the translation as follows. So y hat of t, y. And so with this architecture, tx and ty can be different lengths. And again, you could draw in the A0 there if you want or not. And so this parallel neural network architecture has two distinct parts. There's the encoder, which takes as input, say, a French sentence, and then there's a decoder, which, having read in a sentence, outputs the translation into a different language. So this would be an example of a many-to-many architecture. So by the end of this week, you have a good understanding of all the components needed to build these types of architectures. And then technically, there's one other architecture which we'll talk about only in week 4, which is attention-based architectures, which maybe isn't cleanly captured by one of the diagrams we've drawn so far. So to summarize the wide range of RNN architectures, there is one-to-one. Although if it's one-to-one, we could just get rid of this, and this is just a standard generic neural network. Really don't need an RNN for this. But there is one-to-many. So this was music generation or sequence generation as an example. And then there's many-to-one. That would be an example of sentiment classification, where you might want to read as input all the text with a movie review and then try to figure out, did they like the movie or not. There is many-to-many, so the name entity recognition example we've been using was this, where tx is equal to ty. And then finally, there's this other version of many-to-many, where for applications like machine translation, tx and ty no longer have to be the same. So now you know most of the building blocks for building pretty much all of these neural networks, except that there are some subtleties with sequence generation, which is what we'll discuss in the next video. So I hope you saw from this video that using the basic building blocks of an RNN, there's already a wide range of models that you might be able to put together. But as I mentioned, there are some subtleties to sequence generation, which you get to implement yourself as well in this week's program exercise, where you implement a language model and hopefully generate some fun sequences or some fun pieces of text. So what I want to do in the next video is go deeper into sequence generation. Let's see the details in the next video. Language modeling is one of the most basic and important tasks in natural language processing. It is also one that RNNs do very well. In this video, you learn about how to build a language model using an RNN, and this will lead up toward a fun programming exercise at the end of this week where you build a language model and use it to generate Shakespeare-like text and other types of text. Let's get started. So what is a language model? Let's say you're building a speech recognition system and you hear the sentence, "The apple and pear salad was delicious." So what did you just hear me say? Did I say the apple and pear salad? Or did I say the apple and pear salad? You probably think the second sentence is much more likely, and in fact that's what a good speech recognition system would output, even though these two sentences sound exactly the same. And the way a speech recognition system picks the second sentence is by using a language model, which tells it what is the probability of either of these two sentences. For example, a language model might say that the chance of the first sentence is 3.2 by 10 to the negative 13, and the chance of the second sentence is, say, 5.7 by 10 to the negative 10. And so with these probabilities, the second sentence is much more likely by over a factor of 10 to the 3 compared to the first sentence, and that's why a speech recognition system would pick the second choice. So what a language model does is, given any sentence, its job is to tell you what is the probability of a sentence, of that particular sentence. And by probability of sentence, I mean if you were to pick up a random newspaper, open a random email, or pick a random web page, or listen to the next thing someone says, that a friend of you says, what is the chance that the next sentence you read somewhere out there in the world will be a particular sentence, like the apple and pear salad? And this is a fundamental component for both speech recognition systems, as you've just seen, as well as for machine translation systems, where translation systems want to output only sentences that are likely. And so the basic job of a language model is to input a sentence, which I'm going to write as a sequence, y1, y2, up to yty. And for language model, it'll be useful to represent the sentences as outputs y rather than as inputs x. But what a language model does is it estimates the probability of that particular sequence of words. So how do you build a language model? To build such a model using a RNN, you would first need a training set comprising a large corpus of English text, or text from whatever language you want to build a language model of. And the word corpus is an NLP terminology that just means a large body or a very large set of English text, of English sentences. So let's say you get a sentence in your training set as follows: cat averaged 15 hours of sleep a day. The first thing you would do is tokenize this sentence, and that means you would form a vocabulary, as we saw in an earlier video, and then map each of these words to say one-hot vectors or to indices in your vocabulary. One thing you might also want to do is model when sentences end. So another common thing to do is to add an extra token called EOS, that stands for end of sentence, that can help you figure out when a sentence ends. We'll talk more about this later, but the EOS token can be appended to the end of every sentence in your training set if you want your model to explicitly capture when sentences end. We won't use the end of sentence token for the programming exercise at the end of this week, but for some applications, you might want to use this. And we'll say later where this comes in handy. So in this example, we have y1, y2, y3, 4, 5, 6, 7, 8, 9. 9 inputs in this example if you append the end of sentence token to the end. And during the tokenization step, you can decide whether or not the period should be a token as well. In this example, I'm just ignoring punctuation, so I'm just using day as another token and omitting the period, but you want to treat the period or other punctuation as an explicit token, then you can add the period to your vocabulary as well. Now, one other detail would be, what if some of the words in your training set are not in your vocabulary? So if your vocabulary uses 10,000 words, maybe the 10,000 most common words in English, then the term Mao, as in the Egyptian Mao is a breed of cat, that might not be in one of your top 10,000 tokens. So in that case, you could take the word Mao and replace it with a unique token called UNK, which stands for unknown word, and we just model the chance of the unknown word instead of the specific word Mao. Having carried out the tokenization step, which basically means taking the input sentence and mapping it to the individual tokens or the individual words in your vocabulary, next let's build an RNN to model the chance of these different sequences. And one of the things we'll see on the next slide is that you end up setting the inputs xt to be equal to y of t minus 1. But you see that in a little bit. So let's go on to build the RNN model, and I'm going to continue to use this sentence as the running example. This will be the RNN architecture. At time 0, you're going to end up computing some activation A1 as a function of some input x1, and x1 would just be set it to the set of all zeros, to a zero vector. And the previous A0 by convention also set that to a vector of zeros. But what A1 does is it will make a softmax prediction to try to figure out what is the probability of the first word y. And so that's going to be y1. So what this step does is really, it has a softmax that's trying to predict what is the probability of any word in your dictionary. What's the chance that the first word is A, what's the chance that the first word is Aaron, and then what's the chance that the first word is cats, all the way up to what's the chance the first word is Zulu, or what's the chance that the first word is an unknown word, or what's the first chance that the first word is the end of sentence token, which shouldn't happen really, right? But so y hat 1 is output according to a softmax. It just predicts what's the chance of the first word being whatever it ends up being. And in our example, it wound up being the word cats. So this would be a 10,000 way softmax output if you have a 10,000 word vocabulary, or 10,002, I guess, if you count unknown word and the sentence as 2 additional tokens. Then the RNN steps forward to the next step and has some activation A1 to the next step. And at this step, its job is to try to figure out what is the second word. But now we will also give it the correct first word. So we'll tell it that, gee, in reality, the first word was actually cats, so that's y1. So tell it cats. And this is why y1 is equal to x2. And so at the second step, the output is again predicted by a softmax. The RNN's job is to predict what's the chance of it being whatever word it is. Is it A or Aaron or cats or Zulu or unknown word or EOS or whatever, given what had come previously. So in this case, I guess the right answer was average, since the sentence starts with cats average. And then you go on to the next step of the RNN, where you now compute A3. But to predict what is the third word, which is 15, we can now give it the first 2 words. We're going to tell it cats average are the first 2 words. So this next input here, x3, will be equal to y2. So the word average is input, and this job is to figure out what is the next word in the sequence. So in other words, trying to figure out what is the probability of any word in the dictionary given that what just came before was cats average. And in this case, the right answer is 15, and so on. Until at the end, you end up at, I guess, time step 9, you end up feeding it x9, which is equal to y8, which is the word day. And then this has a9, and its job is to output y hat 9, and this happens to be the EOS token. So what's the chance of whatever it is given, everything that's come before, and hopefully you'll predict that there's a high chance of an EOS end of sentence token. But so each step in the RNN will look at some set of preceding words, such as given the first 3 words, what is the distribution over the next word. And so this RNN learns to predict one word at a time, going from left to right. Next, to train this neural network, we're going to define the cost function. So at a certain time t, if the true word was yt and the neural network softmax predicted some y hat t, then this is the softmax loss function that you should already be familiar with. And then the overall loss is just the sum over all time steps of the losses associated with the individual predictions. And if you train this RNN on a large training set, what it will be able to do is, given any initial set of words, such as cats average 15 or cats average 15 hours of, it can predict what is the chance of the next word. And given a new sentence, say y1, y2, y3, with just 3 words for simplicity, the way you can figure out what is the chance of this entire sentence would be, well, the first softmax tells you what's the chance of y1. That would be this first output. And then the second one can tell you what's the chance of p of y2 given y1. And then the third one tells you what's the chance of y3 given y1 and y2. And so it's by multiplying out these 3 probabilities, and you see much more of the details of this in the programming exercise, but it's by multiplying out these 3 that you end up with the probability of this 3-word sentence. So that's the basic structure of how you can train a language model using an RNN. If some of these ideas still seem a little bit abstract, don't worry about it. You get to practice all of these ideas in the programming exercise. But next, it turns out one of the most fun things you could do with a language model is to sample sequences from the model. Let's take a look at that in the next video. After you've trained a sequence model, one of the ways you can informally get a sense of what is learned is to have it sample novel sequences. Let's take a look at how you could do that. So remember that a sequence model models the chance of any particular sequence of words as follows. And so what we like to do is sample from this distribution to generate novel sequences of words. So the network was trained using this structure shown at the top. But to sample, you do something slightly different. So what you want to do is first sample what is the first word you want your model to generate. And so for that, you would input the usual x1 equals 0, a0 equals 0. And now your first time step will have some softmax probability over possible outputs. So what you do is you then randomly sample according to this softmax distribution. So what the softmax distribution gives you is, it tells you what is the chance that the first word is A, what's the chance the first word is Aaron, what's the first chance the first word is Zulu, what's the chance the first word is the unknown word token, or maybe what's the chance is a end of sentence token. And then you take this vector and use, for example, the numpy command np.random.choice to sample according to the distribution defined by this vector probabilities, and that lets you sample the first word. Next, you then go on to the second time step. And now, remember that the second time step is expecting this y1 as input. But what you do is you would then take the y1 hat that you just sampled and pass that in here as the input to the next time step. So whatever word you just chose for the first time step, pass it as input in the second position, and then this softmax will make a prediction for what is y hat 2. So as a concrete example, let's say that after you sample the first word happened to be the, which is a very common choice of first word, then you pass in the as x2, which is now equal to y hat 1. And now you're trying to figure out what is the chance of whatever the second word is, given that the first word is D. And this is going to be y hat 2. Then you again use this type of sampling function to sample y hat 2. And then at the next time step, you take whatever choice you had represented, say as a one-hot encoding, and pass that to the next time step, and then you sample the third word, take that, whatever you chose, and you keep going until you get to the last time step. And so how do you know when the sequence ends? Well, one thing you could do is if the end of sentence token is part of your vocabulary, you could keep sampling until you generate the EOS token, and that tells you you've hit the end of a sentence and then you can stop. Or alternatively, if you did not include this in your vocabulary, then you can also just decide to sample 20 words or 100 words or something, and then keep going until you've reached that number of time steps. And this particular procedure will sometimes generate a unknown word token. If you want to make sure that your algorithm never generates this token, one thing you could do is just reject any sample that came out as unknown word token and just keep resampling from the rest of the vocabulary until you get a word that's not an unknown word. Or you could just leave it in the output as well if you don't mind having an unknown word output. But so this is how you would generate a randomly chosen sentence from your RNN language model. Now, so far we've been building a word level RNN, by which I mean the vocabulary are words from English. Depending on your application, one thing you could do is also build a character level RNN. So in this case, your vocabulary would be just the alphabets up to Z, and as well as maybe space, punctuation if you wish, the digits 0 to 9, and if you want to distinguish between uppercase and lowercase, you could include the uppercase alphabets as well. And one thing you could do is actually just look at your training set, corpus, and look at the characters that appear there and use that to define your vocabulary. And if you build a character level language model rather than a word level language model, then your sequence Y1, Y2, Y3 would be the individual characters in your training data rather than the individual words in your training data. So for our previous example, the sentence cats average 15 hours of sleep a day. In this example, C would be Y1, A would be Y2, T would be Y3, the space would be Y4, and so on. Using a character level language model has some pros and cons. One is that you don't ever have to worry about unknown word tokens. In particular, a character level language model is able to assign a sequence like Mao a non-zero probability, whereas if Mao was not in your vocabulary for the word level language model, you just have to assign it the unknown word token. But the main disadvantage of the character level language model is that you end up with much longer sequences. So many English sentences will have 10 to 20 words, but may have many dozens of characters. And so character language models are not as good as word level language models at capturing long range dependencies between how the early parts of the sentence also affect the later part of the sentence. And character language models are also just more computationally expensive to train. So the trend I've been seeing in natural language processing is that for the most part, word level language models are still used, but as computers get faster, there are more and more applications where people are, at least in some special cases, starting to look at more character level models. But they do tend to be much harder and much more computationally expensive to train, so they're not in widespread use today, except for maybe specialized applications where you might need to deal with unknown words or other vocabulary words a lot. Or they're also used in more specialized applications where you have a more specialized vocabulary. So armed with these methods, what you can now do is build an RNN to look at the corpus of English text, build a word level, build a character language model, or build a word level or build a character level language model, and then sample from the language model that you've trained. So here are some fun examples of text that was sampled from a language model, actually from a character level language model. And you get to implement something like this yourself in the program exercise. If the model was trained on news articles, then it generates text like that shown on the left. And this looks vaguely like news text, not quite grammatical, but maybe sounds a little bit like things that could be appearing in the news. Concussion epidemic, to be examined. And it was trained on Shakespearean text, and it generates stuff that, sounds like Shakespeare could have written it. The mortal moon hath an eclipse in love, and subject of this thou art another this foe. When best to be my love, to me see salves, for whose are ruse of mine eyes heaves. So that's it for the basic RNN and how you can build a language model using it, as well as sample from the language model that you've trained. In the next few videos, I want to discuss further some of the challenges of training RNNs, as well as how to address some of these challenges, specifically vanishing gradients, by building even more powerful models of an RNN. So in the next video, let's talk about the problem of vanishing gradients, and then we'll go on to talk about the GRU, gated recurrent unit, as well as the LSTM models. You've learned about how RNNs work and how they can be applied to problems like name entity recognition as well as to language modeling, and you saw how backpropagation can be used to train an RNN. It turns out that one of the problems with the basic RNN algorithm is that it runs into vanishing gradient problems. Let's discuss that, and in the next few videos we'll talk about some solutions that will help to address this problem. So you've seen pictures of RNNs that look like this, and let's take a language modeling example. Let's say you see this sentence, the cat which already ate and maybe already ate a bunch of food that was delicious, was full. And so to be consistent is because cat is singular, it should be the cat was, whereas it was the cats which already ate a bunch of food, was delicious, and the apples and pears and so on were full. So to be consistent, it should be cat was or cats were. And this is one example of when language can have very long-term dependencies, where a word that is much earlier can affect what needs to come much later in the sentence. But it turns out the basic RNN we've seen so far is not very good at capturing very long-term dependencies. To explain why, you might remember from our early discussions of training very deep neural networks that we talked about the vanishing gradients problem. So if this is a very, very deep neural network, say 100 layers or even much deeper, then you would carry out forward prop from left to right and then back prop. And we said that if this is a very deep neural network, then the gradient from this output y would have a very hard time propagating back to affect the weights of these earlier layers, to affect the computations of the earlier layers. And for an RNN, we have a similar problem. You have forward prop going from left to right, and then back prop going from right to left. And it can be quite difficult because of the same vanishing gradients problem for the outputs or the errors associated with the later time steps to affect the computations that are earlier. And so in practice, what this means is it might be difficult to get the neural network to realize that it needs to memorize, did you see a singular noun or a plural noun, so that later on in the sequence it can generate either was or were, depending on whether it was singular or plural. And notice that in English, this stuff in the middle could be arbitrarily long, right? So you might need to memorize the singular plural for a very long time before you get to use that bit of information. So because of this problem, the basic RNN model has many local influences, meaning that the output y hat 3 is mainly influenced by values close to y hat 3. And a value here is mainly influenced by inputs that are somewhat close. And it's difficult for the output here to be strongly influenced by an input that was very early in the sequence. And this is because whatever the output is, whether this got it right, this got it wrong, it's just very difficult for the error to backpropagate all the way to the beginning of the sequence, and therefore to modify how the neural network is doing computations earlier in the sequence. So this is a weakness of the basic RNN algorithm, one which we'll start to address in the next few videos. But if we don't address it, then RNNs tend not to be very good at capturing long-range dependencies. And even though this discussion has focused on vanishing gradients, you will remember when we're talking about very deep neural networks that we also talked about exploding gradients, where doing backprop, the gradients should not just decrease exponentially, they might also increase exponentially with the number of layers you go through. It turns out that vanishing gradients tends to be the bigger problem with training RNNs, although when exploding gradients happens, it can be catastrophic because the exponentially large gradients can cause your parameters to become so large that your neural network parameters get really messed up. So it turns out that exploding gradients are easier to spot because the parameters will just blow up, and you might often see NANs or not in numbers, meaning results of numerical overflow in your neural network computation. And if you do see exploding gradients, one solution to that is to apply gradient clipping. And what that really means, all that means is look at your gradient vectors, and if it is bigger than some threshold, rescale some of your gradient vectors so that it's not too big, so that it's clipped according to some maximum value. So if you see exploding gradients, if your derivatives do explode, or you see NANs, just apply gradient clipping, and that's a relatively robust solution that will take care of exploding gradients. But vanishing gradients is much harder to solve, and it will be the subject of the next few videos. So to summarize, in an earlier course, you saw how if you're training a very deep neural network, you can run into vanishing gradient or exploding gradient problems where the derivative either decreases exponentially or grows exponentially as a function of the number of layers. And an RNN, say an RNN processing data over 1,000 time steps or over 10,000 time steps, that's basically a 1,000 layer or like a 10,000 layer neural network. And so it too runs into these types of problems. Exploding gradients, you could sort of address by just using gradient clipping, but vanishing gradients will take more work to address. So what we'll do in the next video is talk about GRUs, or graded recurrent units, which is a very effective solution for addressing the vanishing gradient problem and will allow your neural network to capture much longer range dependencies. So let's go on to the next video. You've seen how a basic RNN works. In this video, you learn about the gated recurrent unit, which is a modification to the RNN hidden layer that makes it much better at capturing long-range connections and helps a lot with the vanishing gradient problems. Let's take a look. You've already seen the formula for computing the activation at time t of an RNN. Is the activation function applied to the parameter WA times the activations for a previous time step and the current input, and then plus a bias. So I'm going to draw this as a picture. So the RNN unit I'm going to draw as a picture, drawn as a box, which inputs A of t minus 1, the activation for the last time step, and also inputs xt, and these two go together. And after some weights and after this type of linear calculation, if G is a tanh activation function, then after the tanh, it computes the output activation A, and the output activation AT might also be passed to, say a softmax unit or something that could then be used to output y hat t. So this is maybe a visualization of the RNN unit, of the hidden layer of the RNN, in terms of a picture. And I want to show you this picture because we're going to use a similar picture to explain the GRU, or the gated recurrent unit. A lot of the ideas of GRUs were due to these two papers, respectively by Junyang Cheng, Kagler, Gossahir, Kyung-Hun Cho, and Yoshib Zhou. And I'm sometimes going to refer to this sentence, which we've seen in the last video, to motivate that given a sentence like this, you might need to remember the cat was singular to make sure you understand why that was rather than were. Right? So the cat was full, or the cats were full. So as we read in this sentence from left to right, the GRU unit is going to have a new variable called C, which stands for cell, for memory cell. And what the memory cell do is it will provide a bit of memory to remember, for example, whether cat was singular or plural, so that when it gets much further into the sentence, it can still word under consideration whether the subject of the sentence was singular or plural. And so at time t, the memory cell will have some value, c of t. And what we'll see is that the GRU unit will actually output an activation value, a of t, that's equal to c of t. And for now, I wanted to use different symbols, c and a, to denote the memory cell value and the output activation value, even though they're the same. And I'm using this notation because when we talk about LSTMs a little bit later, these will be two different values. But for now, for the GRU, c of t is equal to the output activation, a of t. So these are the equations that govern the computations of a GRU unit. At every time step, we're going to consider overwriting the memory cell with a value c tilde of t. So this is going to be a candidate for replacing c of t. And we're going to compute this using an activation function, tanh, of wc, and so that's the parameter matrix wc, and we'll pass to this parameter matrix the previous value of the memory cell, the activation value, as well as the current input value xt, and then plus a bias. So c tilde of t is going to be a candidate for replacing ct. And then the key, really the important idea of the GRU, it will be that we'll have a gate. So the gate I'm going to call gamma u. This is the capital Greek alphabet gamma subscript u, and u stands for update gate, and this will be a value between 0 and 1. And to develop your intuition about how GRUs work, think of gamma u, this gate value, as being always 0 or 1, although in practice, you compute it with a sigmoid function applied to this. So remember that the sigmoid function looks like this, and so its values are always between 0 and 1. And for most of the possible ranges of the input, the sigmoid function is either very, very close to 0 or very, very close to 1. So for intuition, think of gamma as being either 0 or 1 most of the time. And this alphabet u stands for, so I chose the alphabet gamma for this because if you look at a gated fence, looks a bit like this, I guess, then there are a lot of sort of gammas in this fence. So that's why gamma u we're going to use to denote the gate. Oh, also Greek alphabet G, right? G for gate. So G for gamma and G for gate. And then next, the key part of the GRU is this equation, which is that we have come up with a candidate way. We're thinking of updating C using C tilde, and then the gate will decide whether or not we actually update it. And so the way to think about it is maybe this memory cell, C, is going to be set to either 0 or 1, depending on whether the word you're considering, really the subject of the sentence, is singular or plural. So because it's singular, let's say that we set this to 1, and it was plural, maybe we'll set this to 0, and then the GRU unit will memorize the value of the CT all the way until here, where this is still equal to 1, and so that tells it, oh, it was singular, so use the choice was. And the job of the gate of gamma u is to decide when do you update this value. So in particular, when you see the phrase vcat, you know that you're talking about a new concept. The subject of the sentence is cat. So that would be a good time to update this bit. And then maybe when you're done using it, the cat blah 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 was full, then okay, I don't need to memorize it anymore. I can just forget that. So the specific equation we'll use for the GRU is the following, which is that the actual value of CT will be equal to this gate times the candidate value plus 1 minus the gate times the old value, CT minus 1. So notice that if the gate, if this update value, if this is equal to 1, then it's saying set the new value of CT equal to this candidate value. So that's like over here. Set the gate equal to 1. So go ahead and update that bit. And then for all of these values in the middle, you should have the gate equals 0. So this is saying, don't update it, don't update it, don't update it, just hang on to the old value. Because if gamma u is equal to 0, then this will be 0, and this will be 1, and so it's just setting CT equal to the old value, even as you scan the sentence from left to right. So when the gate is equal to 0, it's saying, don't update it, just hang on to the value, and don't forget what this value was. And so that way, even when you get all the way down here, hopefully you've just been setting CT equals CT minus 1 all along, and it still memorizes that cat was singular. So let me also draw a picture to denote the GRU unit. And by the way, when you look in online blog posts and textbooks and tutorials, these types of pictures are quite popular for explaining GRUs, as well as we'll see later LSTM units. I personally find the equations easier to understand than the pictures, so if the picture doesn't make sense, don't worry about it, but I'll just draw it in case it helps some of you. But so a GRU unit inputs CT minus 1 from the previous time step, and this happens to be equal to AT minus 1. So it takes that as its input, and then it also takes as input XT. Then these two things get combined together, and with some appropriate weighting and some tanh, this gives you C tilde T, which is a candidate for replacing CT. And then with a different set of parameters and through a sigmoid activation function, this gives you gamma u, which is the update gate. And then finally, all of these things combine together through another operation. And I won't write out the formula, but this box here, which I shaded in purple, represents this equation, which we had down there. So that's what this purple operation represents. And it takes as input the gate value, the candidate new value, that's the gate value again, and the old value for CT, right? So it takes as input this, and this, and together they generate the new value for the memory cell. And so that's CT equals A. And if you wish, you could also use this and pass this to a softmax or something to make some prediction for, YT, or Y hat T. So that is the GRU unit, or at least a slightly simplified version of it. And what it's remarkably good at is through the gate deciding that when you're scanning the sentence from left to right, say that that's a good time to update one particular memory cell, and then to not change it until you get to the point where you really need it to use this memory cell that you had set even much earlier in the sentence. And because the sigmoid value, now because the gate is quite easy to set to 0, right? So long as this quantity is a large negative value, then up to numerical round off, the update gate will be essentially 0, very, very, very close to 0. So when that's the case, then this update equation ends up setting CT equals CT minus 1. And so this is very good at maintaining the value for the cell. And because gamma can be so close to 0, it can be 0.00001, or even smaller than that, it doesn't suffer from much of a vanishing gradient problem, because you say gamma is so close to 0 that this becomes essentially CT equals CT minus 1, and the value of CT is maintained pretty much exactly, even across many, 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 many time steps. So this can help significantly with the vanishing gradient problem, and therefore allow a neural network to learn even very long-range dependencies, such as that cat and was are related even if they're separated by a lot of words in the middle. Now, I just want to talk over some more details of how you implement this. In the equations I've written, CT can be a vector. So if you have a 100-dimensional hidden activation value, then CT can be 100-dimensional, say. And so C tilde T would also be the same dimension, and gamma would also be the same dimension as the other things I'm drawing in boxes. And in that case, these asterisks are actually element-wise multiplication. So here, if gamma u, if the gate is a 100-dimensional vector, what it is really a 100-dimensional vector of bits. The value is mostly 0 and 1 that tells you of this 100-dimensional memory cell which are the bits you want to update. And of course, in practice, gamma won't be exactly 0 or 1. Sometimes it'll take values in the middle as well, but it's convenient for intuition to think of it as mostly taking on values that are, exactly 0, pretty much exactly 0, or pretty much exactly 1. And what these element-wise multiplications do is it just element-wise tells the GRU unit which are the bits in your, it just tells your GRU which are the dimensions of your memory cell vector to update at every time step. So you can choose to keep some bits constant while updating other bits. So for example, maybe you'll use one bit to remember the singular or plural cat, and maybe you'll use some other bits to realize that you're talking about food, and so because you talk about eating and talk about food, then you'd expect to talk about whether the cat is full later, right? So you can use different bits and change only a subset of the bits at every point in time. You now understand the most important ideas of the GRU. What I presented on this slide, is actually a slightly simplified GRU unit. Let me describe the full GRU unit. So to do that, let me copy the three main equations, this one, and this one, to the next slide. So here they are, and for the full GRU unit, I'm just going to make one change to this, which is for the first equation, which was calculating the candidate new value for the memory cell, I'm going to add just one term. Let me push that a little bit to the right, and I'm going to add one more gate. So this is another gate, gamma R. You can think of R as standing for relevance. So this gate, gamma R, tells you how relevant is CT minus 1 to computing the next candidate for CT. And this gate, gamma R, is computed pretty much as you expect with a new parameter matrix WR, and then the same things as input XT plus BR. So as you can imagine, there are multiple ways to design these types of neural networks. And why do we have gamma R? Why not just, why not use the simpler version from the previous slides? So it turns out that over many years, researchers have experimented with many different possible versions of how to design these units to try to have longer range connections, to try to have model longer range effects, and also address vanishing gradient problems. And the GRU is one of the most commonly used versions that researchers have converged to and have found as robust and useful for many different problems. If you wish, you could try to invent new versions of these units if you want, but the GRU is a standard one that's just commonly used, although you can imagine that researchers have tried other versions that are similar but not exactly the same as what I'm writing down here as well. And the other common version is called an LSTM, which stands for long short-term memory, which we'll talk about in the next video. But GRUs and LSTM are two specific instantiations of this set of ideas that are most commonly used. Just one note on notation. I tried to define a consistent notation to make these ideas easier to understand. If you look at the academic literature, you sometimes see people, if you look at the academic literature, sometimes you see people use an alternative notation. There would be H tilde, U, R, and H to refer to these quantities as well. But I tried to use a more consistent notation between GRUs and LSTMs, as well as using a more consistent notation, gamma, to refer to the gates, to hopefully make these ideas easier to understand. So that's it for the GRU, for the gated recurrent unit. This is one of the ideas in RNNs that has enabled them to become much better at capturing very long-range dependencies, as made RNNs much more effective. Next, as I briefly mentioned, the other most commonly used variation of this class of ideas is something called the LSTM unit, or the long short-term memory unit. Let's take a look at that in the next video. In the last video, you learned about the GRU, the gated recurrent unit, and how that can allow you to learn very long-range connections in a sequence. The other type of unit that allows you to do this very well is the LSTM, or the long short-term memory unit, and this is even more powerful than the GRU. let's take a look. Here are the equations from the previous video for the GRU. And for the GRU, we had AT equals CT, and two gates, the update gate and the relevance gate, C tilde T, which is a candidate for replacing the memory cell, and then we use the gate, the update gate gamma U to decide whether or not to update CT using C tilde T. The LSTM is an even slightly more powerful and more general version of the GRU, and is due to Sepp Hochreiter and Jürgen Schmidt-Huber. And this was a really seminal paper that had a huge impact on sequence modeling. Although I think this paper is one of the more difficult ones to read, it goes quite a lot into the theory of vanishing gradients. And so I think more people have learned about the details of LSTM through maybe other places than from this particular paper, even though I think this paper has had a wonderful impact on the deep learning community. But these are the equations that govern the LSTM. So we'll continue to have a memory cell C, and the candidate value for updating it, C tilde T, will be this. And so notice that for the LSTM, we will no longer have the case that AT is equal to CT. So this is what we'll use. And so this is just like the equation on the left, except that we've now more explicitly used AT there, or AT minus 1 instead of CT minus 1, and we're not using this gamma R, this relevance gate, although you can have a variation of the LSTM where you put that back in, but maybe the more common version of the LSTM doesn't bother with that. And then we will have an update gate, same as before. So W update, and I'm going to use A T minus 1 here, XT, and then plus BU. And one new property of the LSTM is instead of having one update gate control both of these terms, we're going to have two separate terms. So instead of gamma U and 1 minus gamma U, we're going to have gamma U here and an forget gate, which we're going to call gamma F. So this gate gamma F is going to be sigmoid of pretty much what you'd expect, XT plus BF. And then we're going to have a new outputs gate, which is sigma of WO, and then again, pretty much what you'd expect, plus BO. And then the update value to the memory cell will be CT equals gamma U. Then this asterisk denotes element-wise multiplication. There's a vector-vector element-wise multiplication plus, and instead of 1 minus gamma U, we're going to have a separate forget gate gamma F times C of T minus 1. So this gives the memory cell the option of keeping the old value CT minus 1 and then just adding to it this new value C tilde of T. So use a separate update and forget gates. Right? So this stands for update, forget, and output gates. And then finally, instead of AT equals CT, AT is going to equal to the output gate, element-wise multiply with CT. So these are the equations that govern the LSTM. And you can tell it has 3 gates instead of 2, so it's a bit more complicated, and it places the gates in slightly different places. So here again are the equations governing the behavior of the LSTM. Once again, it's traditional to explain these things using pictures, so let me draw one here. And if these pictures are too complicated, don't worry about it. I personally find the equations easier to understand than the picture, but I'll just show the picture here for the intuitions it conveys. The particular picture here was very much inspired by a blog post due to Chris Olar titled Understanding LSTM Networks. And the diagram drawn here is quite similar to one that he drew in his blog post. But the key things to take away from this picture are maybe that you use AT minus 1 and XT to compute all the gate values. So in this picture, you have AT minus 1 and XT coming together to compute the forget gate, to compute the update gate, and to compute the output gate. and they also go through a tanh to compute C tilde t. And then these values are combined in these complicated ways with element-wise multipliers and so on to get Ct from the previous Ct minus 1. Now, one element of this is interesting is if you hook up a bunch of these in parallel, so that's one of them, and you connect them, connect these temporally. So this is the input x1, then x2, x3. So you can take these units and just hook them up as follows, where the output A from a previous time step is the input A at the next time step, and similarly for C. And I've simplified the diagrams a little bit at the bottom. And one cool thing about this you notice is that there's this line at the top that shows how, so long as you set the forget and the update gates appropriately, it is relatively easy for the LSTM to have some value C0 and have that be passed all the way to the right to have, maybe C3 equals C0. And this is why the LSTM, as well as the GRU, is very good at memorizing certain values, even for a long time, for certain real values stored in the memory cell, even for many, many time steps. So that's it for the LSTM. As you can imagine, there are also a few variations on this that people use. Perhaps the most common one is that instead of just having the gate values be dependent only on a t minus 1 xt, sometimes people also sneak in there the value c t minus 1 as well. This is called a peephole connection. Not a great name maybe, but if you see peephole connection, what that means is that the gate values may depend not just on at minus 1 and on xt, but also on the previous memory cell value. And a peephole connection can go into all three of these gates computations. So that's one common variation you see of LSTMs. One technical detail is that these are, say, 100-dimensional vectors if you have a 100-dimensional hidden memory cell unit, and so is this. And the, say, fifth element of Ct minus 1 affects only the fifth element of the corresponding gates. So that relationship is 1-to-1, where not every element of the 100-dimensional Ct minus 1 can affect all elements of the gates, but instead, the first element of Ct minus 1 affects the first element of the gates, the second element affects the second element, and so on. But if you ever read a paper and see someone talk about a peephole connection, that's what they mean, that Ct minus 1 is used to affect the gate value as well. So that's it for the LSTM. When should you use a GRU and when should you use an LSTM? There isn't widespread consensus in this. And even though I presented GRUs first, in the history of deep learning, LSTMs actually came much earlier, and then GRUs were a relatively recent invention that were maybe derived as partly a simplification of the more complicated LSTM model. Researchers have tried both of these models on many different problems, and on different problems, the different algorithms will win out, so there isn't a universally superior algorithm, which is why I want to show you both of them. But I feel like when I am using these, the advantage of the GRU is that it's a simpler model, and so it's actually easier to build a much bigger network that only has 2 gates. So computationally it runs a bit faster, so it scales to building somewhat bigger models. But the LSTM is more powerful and more flexible since it has 3 gates instead of 2. If you want to pick one to use, I think LSTM has been the historically more proven choice. So if you had to pick one, I think most people today would still use the LSTM as the default first thing to try, although I think in the last few years, GRUs have been gaining a lot of momentum, and I feel like more and more teams are also using GRUs because they're a bit simpler, but often work, just as well, and it might be easier to scale them to even bigger problems. So that's it for LSTMs. With either GRUs or LSTMs, you'll be able to build neural networks that can capture much longer range dependencies. By now, you've seen most of the key building blocks of RNNs. But there are just two more ideas that'll let you build much more powerful models. One is bidirectional RNNs, which lets you at a point in time to take information from both earlier and later in the sequence. So we'll talk about that in this video. And the second is deep RNNs, which you see in the next video. So let's start with bidirectional RNNs. So to motivate bidirectional RNNs, let's look at this network, which you've seen a few times before in the context of named entity recognition. And one of the problems of this network is that to figure out whether the third word Teddy is a part of a person's name, it's not enough to just look at the first part of the sentence. So to tell if Y3 should be 0 or 1, you need more information than just the first three words, because the first three words doesn't tell you if they're talking about teddy bears or talking about the former US President Teddy Roosevelt. So this is a unidirectional or forward directional only RNN. And this comment I just made is true whether these cells are standard RNN blocks or whether they're GRU units or whether they're LSTM blocks, right? But all of these blocks are in a forward only direction. So what a bidirectional RNN does, or a BRNN, is fix this issue. So a bidirectional RNN works as follows. And I'm going to use a simplified 4 inputs, or maybe a 4-word sentence. So we have 4 inputs, x1 through x4. So this network's hidden layer will have a forward recurrent components. So I'm going to call this A1, A2, A3, and A4. And I'm going to draw a right arrow over that to denote that it's the forward recurrent component. And so they'll be connected as follows. And so each of these 4 recurrent units inputs the current X and then feeds in to help predict y hat 1, y hat 2, y hat 3, and y hat 4. So far I haven't done anything, right? Basically redrawn the RNN from the previous slide, but with the arrows, placed in slightly funny positions. But I drew the arrows in these slightly funny positions because what we're going to do is add a backward recurrent layer. So we're going to have A1, left arrow to denote this is a backward connection, and then A2, backwards, A3, backwards, and A4, backwards. So the left arrow denotes that this is a backward connection. And so we're then going to connect the network up as follows. And these A backward connections will be connected to each other going backward in time. So notice that this network defines a cyclic graph. And so given an input sequence, x1 through x4, the forward sequence would first compute a forward 1, then use that to compute a forward 2, then a forward 3, then a forward 4, whereas the backward sequence would start by computing a backward 4, and then go back and compute a backward 3, and notice you're computing network activations. This is not back prop, this is forward prop. But the forward prop has part of the computation going from left to right, and part of the computation going from right to left in this diagram. But then having computed a backward 3, you can then use those activations to compute a backward 2, and then a backward 1. And then finally, having computed all your hidden layer activations, you can then make your predictions. And so, for example, to make the predictions, your network would have something like y hat at time t is an activation function applied to wy with both the forward activation at time t and the backward activation at time t being fed in to make that prediction at time t. So if you look at the prediction at time set 3, for example, then information from x1 can flow through here, forward 1 to forward 2, that also takes in information here, to forward 3 to y hat 3. So information from x1, x2, x3 are all taken into account, whereas information from x4 can flow through a backward 4 to a backward 3 to y3. So this allows the prediction at time 3 to take as input both information from the past as well as information from the present, which goes into both the forward and the backward things at this step, as well as information from the future. So in particular, given a phrase like, he said, Teddy Roosevelt, ... to predict whether Teddy is a part of a person's name, you'll be able to take into account information from the past and from the future. So this is the bidirectional recurrent neural network. And these blocks here can be not just the standard RNN block, but they can also be GRU blocks or LSTM blocks. In fact, for a lot of NLP problems, for a lot of text or natural language processing problems, a bidirectional RNN with a LSTM appears to be commonly used. So if you have an NLP problem and you have a complete sentence, you're trying to label things in the sentence, a bidirectional RNN with LSTM blocks, both forward and backward, would be a pretty reasonable first thing to try. So that's it for the bidirectional RNN, and this is a modification that you can make to the basic RNN architecture or the GRU or the LSTM, and by making this change you can have a model that uses RNN or GRU or LSTM and is able to make predictions anywhere even in the middle of the sequence, but take into account information potentially from the entire sequence. The disadvantage of the bidirectional RNN is that you do need the entire sequence of data before you can make predictions anywhere. So for example, if you're building a speech recognition system, then a BRNN will let you take into account the entire speech utterance, but if you use this straightforward implementation, you need to wait for the person to stop talking to get the entire utterance before you could actually process it and make a speech recognition prediction. So for real-time speech recognition applications, there's somewhat more complex models as well, rather than just using the standard bidirectional RNN as you're seeing here. But for a lot of natural language processing applications where you can get the entire sentence all at the same time, the standard BRNN algorithm is actually very effective. So that's it for BRNNs. In the next and final video for this week, let's talk about how to take all of these ideas, RNNs, LSTMs, or GRUs, and the bidirectional versions, and construct deep versions of them. The different versions of RNNs you've seen so far will already work quite well by themselves, but for learning very complex functions, sometimes it's useful to stack multiple layers of RNNs together to build even deeper versions of these models. In this video, you'll see how to build these deeper RNNs. Let's take a look. So you remember, for a standard neural network, you would have an input X, and then that's fed to some hidden layer, and so that might have activations, say A1 for the first hidden layer, and then that's fed to the next layer with activations A2, then maybe another layer, activations A3, and then you make a prediction y hat. So a deep RNN is a bit like this, but taking this network that I just drew by hand and unrolling that in time. So let's take a look. So here's the standard RNN that you've seen so far, but I've changed the notation a little bit, which is that instead of writing this as A0 for the activation at time 0, I've added this square bracket 1 to denote that this is for layer 1. So the notation we're going to use is A square bracket L to denote that it's an activation associated with layer L, and then angle bracket T to denote that that's associated with a time T. So this would have an activation A first layer time 1. This would be a first layer time 2, first layer time 3, first layer time 4. And then we can just stack these things on top. And so this would be a neural network with 3 hidden layers. So let's look at an example of how this value is computed. So A2, 3 has two inputs. It has the input coming from the bottom, and there's the input coming from the left. So it'll be computed as an activation function G applied to a weight matrix. This is going to be WA because it's computing an A quantity, an activation quantity, and for the second layer. And so I'm going to give this A2, 2 as that thing, comma A1, 3 is that thing, plus BA associated the second layer, and that's how you get that activation value. And so the same parameters, WA2 and BA2, are used for every one of these computations at this layer. Whereas in contrast, the first layer would have its own parameters, WA1 and BA1. So whereas for standard neural nets like the one on the left, we've seen neural networks that are very, very deep, maybe over 100 layers. For RNNs, having 3 layers is already quite a lot because of the temporal dimension. These networks can already get quite big, even if you have just a small handful of layers. And you don't usually see this stacked up to be, like 100 layers. One thing you do see sometimes is that you have recurrent layers that stacked on top of each other, but then you might take the output here, let's get rid of this, and then just have a bunch of deep layers that are not connected horizontally, but to have a deep network here that then finally predicts Y1, and you can have the same, deep network here that predicts Y2. So this is a type of network architecture that we're seeing a little bit more, where you have 3 recurrent units that are connected in time, followed by a network after that. This will be same for Y3 and Y4, of course. There's a deep network that does not have the horizontal connection. So that's one type of architecture we seem to be seeing more of. And quite often, these blocks don't just have to be standard RNN, the simple RNN model. They can also be GRU blocks or LSTM blocks. And finally, you can also build deep versions of the bidirectional RNN. Because deep RNNs are quite computationally expensive to train, there's often a large temporal extent already, though you just don't see as many deep recurrent layers. This has, I guess, 3 deep recurrent layers that are connected in time. You don't see as many deep recurrent layers as you would see, number of layers in a deep conventional neural network. So that's it for deep RNNs. With what you've seen this week, ranging from the basic RNN, the basic recurrent unit, to the GRU, to LSTM, to the bidirectional RNN, to the deep versions of this that you just saw, you now have a very rich toolbox for constructing very powerful models for learning sequence models. I hope you enjoyed this week's videos. Best of luck with the programming exercises, and I look forward to seeing you next week. Hello, and welcome back. Last week, you learned about RNNs, GRUs, and LSTMs. In this week, you see how many of these ideas can be applied to NLP, to natural language processing, which is one of the fields of AI that is really being revolutionized by deep learning. One of the key ideas you learn about is word embeddings, which is a way of representing words that lets your algorithms automatically understand analogies like that man is the woman as king is the queen, and many other examples. And through these ideas of word embeddings, you'll be able to build NLP applications even with modestly sized or even with relatively small label training sets. Finally, towards the end of the week, you see how to debias word embeddings. That's to reduce undesirable gender or ethnicity or other types of bias that learning algorithms can sometimes pick up. So let's get started with a discussion on word representation. So far, we've been representing words using a vocabulary of words, and our vocabulary from the previous week might be, say, 10,000 words. And we've been representing words using a one-hot vector. So, for example, if man is word number 5391 in this dictionary, then you represent it with a vector with a 1 in position 5391. And I'm also going to use O subscript 5391 391 to represent this vector, where O here stands for one hot. And then if woman is word number 9853, then you represent it with O subscript 9853, which just has a 1 in position 9853 and zeros elsewhere. And then other words, king, queen, apple, orange would be similarly represented with one hot vectors. One of the weaknesses of this representation is that it treats each word as a thing unto itself, and it doesn't allow an algorithm to easily generalize across words. For example, let's say you have a language model that has learned that when you see I want a glass of orange blank, well, what do you think the next word will be? Very likely to be juice. But even if the learning algorithm has learned that I want a glass of orange juice is a likely sentence, if it sees I want a glass of apple blank, as far as it knows, the relationship between apple and orange is not any closer as the relationship between any of the other words, man, woman, king, queen, and orange. And so it's not easy for the learning algorithm to generalize from knowing that orange juice is a popular thing to recognizing that apple juice might also be a popular thing or a popular phrase. And this is because the inner product between any two different one-hot vectors is 0. If you take any two vectors, say queen and king, and inner product them, the inner product is 0. If you take apple and orange and inner product them, the inner product is 0. And the Euclidean distance between any pair of these vectors is also the same. So it just doesn't know that somehow apple and orange are much more similar than king and orange or queen and orange. So won't it be nice if instead of a one-hot representation, we can instead learn a featurized representation where for each of these words, man, woman, king, queen, apple, orange, or really for every word in our dictionary, we could learn a set of features and values for each of them. So for example, each of these words might have, we want to know what is the gender associated with each of these things. So if gender goes from -1 for male to +1 for female, then the gender associated with man might be -1, for woman might be +1. And then if you're actually learning these things, maybe for king you get -0.5